All right, next I'd like to take a look at some more examples of F equals ma. That's our Newton's second law. Sum of vector forces equals mass times acceleration. And so there are many applications to this, and I just want to kind of dig into them so that we can see how to handle each problem type. So in what we call a two-body problem, it means that there are two objects that are coupled together. Now by coupled here, I mean that they have some kind of contact with each other so that the direct contact forces have a means of communicating to each other directly. And so in a two-body problem, like this one here, we might have a force acting from the left. Let's say that this force is a 10 Newton applied force on to these two masses which are in direct physical contact. So they are coupled together because of their direct physical contact. Other examples of coupling could be, let's say, a string that connects the two masses together. As long as the string doesn't go slack or break, we have coupling there as well, so that they move together as a single object. So in this case, let's say that the large mass, big M, is equal to 1 kilogram, and the little mass is equal to, well, let's make this 2 kilograms, and the little mass, let's make 1 kilogram, just so that the numbers are a little easier to work with. Okay, and let's find in this problem, the contact force between the two masses and also the acceleration of the system. So that's also the acceleration of each mass, because each mass is moving, each of the masses are moving together. So have the acceleration of each mass, and this is also the system acceleration. So how to go about this? Well, what we want to do is really break this up into two vector diagrams. One that involves the sum of the forces acting on big M, and the second equation being a free body diagram that contains all of the forces acting on the second mass. So for the first mass, big M, do the sum of the forces equals mass times acceleration. Now we'll note here that there actually are forces acting in the vertical direction too, that we're not even really considering here. We have a normal force due to mass 1 and a force big mg, and then we also have a smaller normal force for the little mass and a smaller mass, little mg. And so those forces are going to cancel out, but we'll assume here there's no friction. Okay? And so if there's no friction, then the normal force doesn't really affect the horizontal x motion because it's moving on a frictionless surface. So only the forces that are acting in the x direction are really relevant in this problem to finding the acceleration. On future problems, we will look at friction, which makes the problem more realistic, of course, because most objects do experience friction unless you're on a subatomic level where friction doesn't act because it's a molecular force. But here, we just start with some simple problems where there's no friction. Okay, so in the x direction then, the sum of the forces acting on big M, let's just see how that would work. Here, notice that what I'm doing here is I'm replacing little m by a contact force because big M has to push into little m, but little m has from Newton's first law, inertia, right? So that means that it pushes back. So the fact that big M pushes on little m means that little m pushes back on big M with an equal and opposite reaction force, which we could call the contact force. And then coming in from the left, we have the big force, big F. Okay, so we can write here then that the sum of the x forces are big F minus F contact equals big M times A. Okay, so this is the sum of the forces acting on this mass equals that mass times the acceleration. And notice here that there's also a force of big M acting on little m, but we're not interested in that here. We're only interested in the forces that are acting on this mass only. That's it. And so we keep all the other forces out of the diagram just to simplify things so that we don't get confused. And then for little m, we can separate that out. And there's only one force acting on little m in the x direction. Of course, the vertical forces are canceling. There's no friction. So we can say that F contact equals little m times A. Okay, so what we can do from this point then is to take the two equations, which I can call equation 1 and equation 2. I'll write them right next to each other, and we can solve them simultaneously. Okay, so that's what we want to do here. F minus Fc equals big M A, and F contact equals little m A. Okay, now mass times acceleration is not a force. By Newton's second law, that's the sum of forces. Okay, so that's important because a lot of times I'll be looking at people's work and they'll say the MA force. And that's not real. That's not what Newton's second law is telling us. Newton's second law is telling us that the sum of the forces equals the object's mass times its acceleration. So this is not a force. This is, by definition, the sum of all forces. Okay, and so if we then take these two equations, since we don't know either the acceleration or the mass, let's just add the two equations, the acceleration or the contact force. Let's just add the two equations together. So that'll give me F plus minus F contact is equal to M1A, little m-A, plus big M-A. So that gives us little m plus big M times A. Okay, so this is really equivalent then to saying that both masses are a single combined mass for the purposes of figuring out the acceleration of the system. And that would be valid. There's no reason why you can't do that. And so you go, well, if I'm treating it like a combined mass, then why do I have to split it up into two separate parts? That looks more confusing. Well, the key thing here is you can't get the contact force unless you separate them out. And so that's an important part of this problem, is finding the contact force. So, but because of the way the algebra worked here, it was a little easier for me to get the acceleration first. So my acceleration then, A, is just equal to big F divided by big M plus little m, or that's equal to 10 newtons divided by 2 kilograms plus 1 kilogram, or that's 10 newtons divided by 3 kilograms. And so that's going to give us 10 thirds, or 3.33 meters per second squared. So that's the acceleration of both masses, because they're both moving together. So the amount that one moves is exactly the same as the amount that the other moves. So that takes care of the acceleration. Then, my second unknown here, and you always want to be thinking this way, do I have the right number of equations for how many unknowns I have? In this case, We don't know the contact force, we don't know the accelerations, and we have two equations, so we're good. Okay, and so the second part of this then would just be to plug in this case to the easier equation. All right, Fc equals little ma, that's 1 kilogram, times 3.33 meters per second squared, or that gives us 3.33 newtons for F contact. Okay, so that's our general procedure then for solving this kind of a problem, where we have two masses that are coupled together. Now, you might wonder, well, what if I change places? I put little m here and big M there. Would that change the acceleration? What do you think? If I just switch the masses but keep the force pushing from the left? No, it wouldn't change the acceleration. But would it change the contact force? The answer is yes, it would change the contact force, because the big mass only has to push a smaller mass up along here. And so that means it doesn't have to push as hard on little m. But if little m was first, then it would have to push much harder on big M, and then big M would have to push back with an equal and opposite reaction force to resist that. And so it turns out the contact force, and you can double check this by working that problem out, would be double what it is in this problem. So here, with the original problem, you can see that there's an action force. This is the force of big M on little m. Then there's a reaction force. That's the force of little m on big M. But you notice that the force of little m on big M is in this picture and not in this picture, because this mass can't exert a force on itself. That's like you trying to pick yourself up by your bootstraps. It just, everything cancels out. It doesn't work out. Okay, and so these masses then can exert forces on other masses, but not on themselves. Okay. And so if we look up at the data projector for a moment, we see that we've looked at a couple of examples now of direct contact forces. We also looked at one example of a field force that had to do with the acceleration due to gravity. But that also had direct contact forces in it. So sometimes you'll get a problem like that elevator problem that has both contact forces and field forces in them at the same time. And now there, in general, for field forces, which are the ones that act at a distance, there are four main known forces. There's the strong force that holds together the nucleus of an atom. It holds protons in the nucleus and neutrons. The electromagnetic force, which acts between charged particles. The electroweak force, which causes nuclear decay, and the gravitational force. Now we'll mention some of the electric forces when we talk about the states of matter. But for the moment, for the most part, we'll just be dealing with gravitational forces as our long-range forces in this class. And then we'll get to the electromagnetic force in Physics 2.8b, and then we'll do the strong force and the electroweak force and try to link them all together in 2.8c. Okay. And as we mentioned before, a Newton is the force that must be exerted to accelerate 1 kilogram of mass with an acceleration of 1 meter per second squared. Okay. Now, when objects, and you have or will see this in lab, if you haven't seen it already, if you're in free fall, you have a small mass, little m, or a big mass, big M, they fall at the same rate, at the same acceleration, and that acceleration is equal to g. Now, can we understand that in terms of Newton's second law? The answer is yes, because our weight is equal to mg. So that means that g is equal to, in this case, it's going to be a small weight divided by a small mass. In this case, G is going to be a big weight divided by a big mass. So even though there's more force acting on the object, there's also proportionally more mass because the force is directly proportional to the mass. So this is the reason why they both fall at the same rate under the influence of gravity, unless there's air resistance. And of course, air resistance can make a big difference. We look back up at the data projector here. We see a feather falling at the same rate as this apple, but that would have to be an evacuated tube in which we have no air resistance, because air resistance is an external force, and that external force is much more significant on a light object that is exposing a lot of surface area to the air than it is for a heavy object. But we have a good picture of Neil Armstrong dropping a hammer and a small pebble on the surface of the moon. And in that vacuum of space, they both fall at exactly the same rate. And actually, he also took a feather, what they call the falcon feather, and dropped it right along with the mass, and they both fell just like what you're seeing here in this picture. So that was back in 1969 that was done. Okay, so here we can see then that if we apply a force, we get a certain acceleration. If we apply twice that force to the same mass, we get double the acceleration. If we apply half as much force, we get half of the acceleration if we're acting on the same mass. But if we apply the same force to progressively larger masses, the acceleration will go down. So if the sum of the forces is equal in these three on the right, then what's going to happen is that the acceleration, which is a vector, will progressively get smaller, because the acceleration is the sum of the forces divided by the mass. If the force stays constant and the mass gets bigger, then the acceleration must go down. Okay, so those are two cases that we often look at. One where we have differing forces acting on the same mass, but in the other case we have the same force acting on differing masses. Okay, so when we're drawing a free body diagram, we can look at every aspect of the problem and try to draw a perfect picture. That can be very confusing and extremely time-consuming. And so instead of trying to draw something that takes into account every part of the system, it's easier to just identify which point we're looking at the sum of the forces. In this case, it might be the cart that is being carried by the horse. And then simplify the different forces that are acting just by little vector arrows. And that, although it's not as artistic looking as this, it's actually a little easier to follow when you're trying to solve the physics equations. And so that's what we try to do then, is find the object that the forces are acting on, and then just draw the forces that are associated with what's acting on that mass and not anything else. We don't want the force, in this case of the cart, on the horse. Okay? We just want the force of the horse on the cart, because we're looking at the acceleration, in this case, of the cart. And so that is something that we have to get used to, is you don't necessarily always want to draw every force into the problem. Now, the next thing that I'd like to talk about, just briefly, so that we can solve other problems. This actually gets a little bit into chapter 5, but that's okay, because I like to cover it all at once, so I don't have to go back to it and then redo the same problems with friction later. We can think of friction as being a dissipative force. It is associated with a contact force between objects. and can be broken up into two separate categories. We have the static force, which we'll talk about a little bit later, and what I want to talk about now is kinetic friction. Now in kinetic friction, the object is moving and the two surfaces are rubbing against each other. And these surfaces are kind of jaggly. Even if you were to look at two objects on a fairly small scale, they might look like they are smooth. But what we see here is that this is actually, these surfaces only come in contact in a very few select points. And so those points then rub against each other, and then hills fall into valleys, and so that creates a resistive force depending on how jaggly the surfaces are. And so we can write then the kinetic friction is equal to what we call the coefficient of kinetic friction times the normal force. So this coefficient of friction is associated with the roughness of the surfaces. And the normal force is simply the force with which the surfaces are being pressed together. So that a lot of times this normal force would just be equal to the weight of the object if we have, for example, a mass sitting on a level surface. Let's say this big mass is 1 kilogram, and here we have a weight force, mg. Here we have a normal force, Fn. And then we start sliding this thing across the table this way. So we start out with an initial velocity, let's say, of 3 meters per second. And it's moving to the right, like this. Okay? We already know what's going to happen with that. Just the same thing that might happen with this calculator here. I slide this calculator along, and it comes to rest on that surface because of friction. And so the same thing will happen here. There'll be a negative acceleration, and associated with that, a negative force due to friction. Now, we need the coefficient of friction to solve this problem. The coefficient of friction is a number. Typically, it's a number between 0 and 1, but that's not always the case. Here on the data projector, we can see a few coefficients of friction and this is kinetic. When we get to static friction later, I'll talk more about these. But we might notice here, even though we haven't discussed static friction yet, that the coefficient of static friction is generally bigger than the coefficient of kinetic friction for a given substance. And so aluminum on steel, then it'd be 0.47, steel on steel, 0.57. But then you get to ice on ice, Okay, that'd be 0.03. Waxed wood on wet snow, 0.1. Waxed wood on dry snow, 0.04. Okay, so when you're skiing then, you don't have a lot of friction to deal with, and that's why you're able to get going pretty fast on the ski slopes. Wood on wood would be around 0.2. And so this is just an indication then of how rough the surfaces are. If you had something where it was sandpaper on sandpaper, that might be more than 1. Okay, so it is possible to have these numbers be more than 1, but generally they tend to be a number between 0 and 1. And so for our example here, let's say that the coefficient of kinetic friction, just because it's an easy number to work with, is 0.5. And then let's ask here, how far does the mass slide before coming to rest? All right, so we're actually going to dig back into our kinematics equations here. Because first we'll calculate the acceleration, and then we have to go back and figure out what distance x is going to be associated with this thing, ending up with a final velocity of 0. Okay. So in this problem then we can see that if we're just looking at the kinematics problem, and we want to know how far it slides, and there's a negative acceleration that's unknown, then we only know 2 out of 5. So solving our dynamics problem will give us the third of our 5 that we need to solve the problem, and then we can just go ahead and find the right kinematics equation with which to solve for our unknown, which in this case is the displacement, the distance that it slides. So what we want to do first then is look at the free body diagram. And so the free body diagram has nothing to do with the initial velocity. That's not a force vector. But it does have to do with the normal force in mg now, because mg determines the normal force for this problem. So we can say the sum of the y forces equal to F normal minus mg, that's equal to 0. So that tells us then from the sum of the y forces that we have equal and opposite forces acting, but no acceleration. So the normal force is equal to the weight, mg. Okay, I was using capital M here, so let me just keep using that. But now we need to know what the force is acting in the x direction, so that's just our force of friction. So in the x direction, we have a separate equation. So we have one y equation force for the y parts of the force, and we have one x equation force for the x parts of the force. So this is the sum of the x forces equals mass times acceleration. And there's only one x force. That's negative. It's moving this way. So you do need to know that it's moving this way to know that the direction of the friction force is in the opposite direction. Okay? But that's all that you need this for. You don't need to know the value of the velocity to get the correct free body diagram. And so I'll write that over here. Pretty simple equation. We have the x force is negative because we'll define the positive direction to be the direction of motion. And you should always do that because you don't want friction forces being positive. It just makes things more confusing. So we can say that minus mu k times the normal force equals ma. Or minus mu k times big mg equals big ma. And this came from solving the y equations and getting that the normal force was equal to the weight. Now, will the normal force always be equal to the weight? The answer is no. There are going to be situations where you'll have other forces acting at an angle, and we'll look at some of those really soon. But in this case, it is true. And so what we can do then is just cancel out the masses, and that gives us the acceleration is minus mu k times g. Or, if we'd use 10 for g, that's going to be minus 0.5 times 10 meters per second squared, and that gives us minus 5 meters per second squared. Okay, so that's our acceleration now. Now that we have the acceleration, we can set up a kinematics equation with knowns and unknowns, just like before. I hope you've gotten used to doing this at this point, because everything keeps building on what we've learned before. So here, our initial velocity is 3 meters per second. The final velocity at the point that it stops is 0. And the acceleration is minus 5 meters per second squared. The unknowns are the time of flight and the x displacement. And so I can eliminate then all of the kinematics equations involving the time. And if you look at your list, that leaves us with v final squared equals v initial squared plus 2ax. And so that's enough information with what we have here to solve for the displacement of the mass. But notice that we couldn't have done it without our dynamics problem. This is the dynamics part where we used the free body diagram to obtain an expression for the acceleration by knowing the definition of a friction force. So that this gives us 0 is equal to 3 meters per second squared plus 2 times minus 5 meters per second squared times x. Okay, and then dropping the units and bringing the negative over to the other side, we get 10x equals 9, or x equals 0.9 meters. So that's how far the mass moves along the surface, not quite a meter, 90 centimeters, before coming to rest. And so with the problem, the way that I've got it set up here, I actually have about the right distance going there for it. A meter is maybe about this long, something like that. And so that's the way then that you would handle a problem if there was just friction acting. But now let's expand on this a little bit and say that we have several forces, including friction, acting. In this next example, let's take a look at a mass. In this case, let's make the mass equal to 10 kilograms. Let's have a string coming off of the mass, which is pulling up with a tension that's equal to 100 newtons. Okay? And let's make this angle 30 degrees from the horizontal. And let's allow this mass then to be pulled along the surface of this table with an acceleration a that needs to be determined. Okay, so we want to find the acceleration if the coefficient of kinetic friction on the surface, again, is 0.5. Okay, so that is our problem. And so this is a one-body problem. But what makes this a little trickier than the other one-body problems that we've looked at so far is that the forces, there are more forces, first of all. We're going to have a friction force here, and that's going to be tending to oppose the applied force as this mass moves in this direction. And so this would be our force of friction. And we also have the weight force here, big mg. And we have a normal force here, but that normal force is not necessarily now equal to the weight. Because you can see here that this force that's coming off at a 30-degree angle has components to it, so that only the x component pulls the mass forward. Fx is equal to F cosine 30. And the y component helps to lighten the load on the normal force. So in other words, the surface doesn't have to lift up on the mass as much, because a part of the string force is helping to lighten the load. And so Fy then is equal to F sine 30. Okay, and so our goal then is to find the acceleration, and we're given that the coefficient of kinetic friction is 0.5. So one mistake that people often make is to just automatically, in a problem like this, think that the normal force is equal to the weight, because we've seen that in other examples where there haven't been any other vertical forces acting. But that's not the case here, because Fy, the y part of this tension force, is helping to support the weight. And so if I were going to draw this to scale, I'd probably make this a little bigger. So this is a pretty big value, then this is a somewhat smaller value, but the sum of these two, F normal plus Fy, should equal mg, because they have to be equal and opposite. Okay, and so it's important to see that before we really get started with the problem. If you don't see that that's the case, then when we decompose this force vector into x and y components, only the x part pulls it to the right, and the y part helps to lighten the load. Okay, so that is an important concept to get before you can write the equations correctly. And we have two equations to work with now, because we've got the sum of the y forces are equal to 0, and the sum of the x forces equal to mass times acceleration. And this is x acceleration, because there is no y acceleration. So I just leave it as a, because it's just kind of assumed that we know that it's in x. And so implicitly then, we've assumed an xy coordinate system that is positive to the right and also positive in the vertical direction. Okay, so we want to be careful now when we do this. To solve for the y equations, we use this to get the normal force. And we need the normal force because we have friction. And friction is the coefficient of kinetic friction times the normal force. So we, as I said before, we don't want to just jump into this and say that the normal force is equal to the weight, because it's not. We'll find that out in a second here. So we have Fy, which is F sine 30, plus F normal equals, or minus, I should say, mg equals 0. Okay, so these are the positive forces, Fy and F normal. This is the negative force, mg. And those are the forces that are acting in the y direction, so they have to add up to 0. So our normal force then is going to be equal to mg minus F sine 30. So for this problem, that's going to be, well, m is 10 kilograms times g, 10 meters per second squared, minus 100 newtons for the force. So here I'm plugging in the numbers, times the sine of 30. All right, so with our trusty 30, 60, 90 right triangle, 1, 2, root 3, we see that the sine of 30 is 1/2. Okay, so this is going to be 10 times 10 minus 100 times 1/2. So that's 100 minus 50, or 50 newtons. Okay, so the weight was 100 newtons, but the normal force is only half of that, meaning that the tension in the string, if it's pulling at a 30-degree angle, is going to be doing half the lifting. And the normal force will do the other half of the lifting to support the mass against gravity. This also tells us how hard the surfaces are being pushed together so that we can determine the value for the friction force. Okay, so the sum of our x forces then, this is what gives us the acceleration. So we have then fx, which is f cosine 30 minus mu k times the normal force for the friction force here is equal to ma. So that's our sum of the x forces. We have two. We have the fx force, and we have the negative friction force here. And then we plug in numbers. This is going to be 100 cosine of 30 is root 3 over 2 minus mu k, which is 0.5, times the normal force, which we got here, that's 50. Right? Okay, so that goes in here. So it's like two equations and two unknowns. Equals m, which is 10 kilograms, times a. All right, so be sure that you understand how that works. And then in the last step, we can solve for the acceleration. And so I'll drop the units in the last step. This is going to be 100 times 0.866 minus 25 over 10 equals a. All right, so that's 86.6 minus 25. Over 10. Okay, so that it'd be what? 61.6 over 10? 80, 25, 60, 80, yeah. So that would give us 6.16 meters per second squared. For our acceleration. And so this is a problem then in which we didn't know the acceleration. We needed this equation for that. We didn't know the normal force, so we needed this equation for that. And then we could solve those two simultaneously. We eliminated the normal force from the vertical equation, plugged that into the horizontal equation, and just solved down to one equation and one unknown. Okay. Now, if in this original problem, the mass was being pulled by the force at 100 newtons horizontally, like this, then you would think it would be going faster. But then also the friction force would increase, because the normal force would go to its maximum value. So you'd have more slowing it down. So even though it might be going a little bit faster, if all of the force was oriented horizontally like this, it might not be going as much faster as you would think. And there are certain values for the friction force where it would actually be going slower if you lowered it to that point and you had a bigger friction force because of the coefficient, say, being 0.9 or 1.5 or something, if it was something really radical. than like if you're driving on gravel or something, or sliding this thing on gravel. Yeah, it might be quite a bit larger force. Okay.